Good morning, everybody. By 2050, global food demand is expected to increase by about 60%. By then, agriculture will need to feed around 10 billion people under increasing water scarcity. So, my research focuses on how long-term organic management enhances soil water storage and hydraulic functions in no-till systems. Let's start with the context and importance. Water availability in soil is a fundamental control on plant growth, productivity, and ecosystem resilience. Soil acts as a dynamic reservoirs, balancing rainfall, evaporation, and root uptake. In agricultural systems, plant available water capacity determines crop yield stability and drought tolerance. Degradation of soil structure due to tillage or loss of organic matter reduce infiltration and water storage capacity. The rationales: long-term no-till systems with organic amendments are known to enhance soil physical quality. However, the quantitative relationship between the management practices and plant available water capacity are poorly understood. Understanding how soil structure, pore size distribution, and organic matter stabilization interact is crucial for climate resilience water management. Let's talk about some key concepts. Bulk density represents the mass of dry soil per unit bulk volume. Soil with lower bulk density usually have better aeration. Total porosity is the fraction of total soil volume occupied by pores, and it's derived from bulk density and particle density. Some other key concepts: pore size distribution. It could be transmission pore, storage pore, and residual pore. The objective of the study was to evaluate the long-term impact of using organic amendments and cover cropping on plant available water capacity under a no-till cropping system in a temperate agroecosystem. The hypothesis was long-term application of organic amendments, particularly manure and compost, significantly enhance plant available water capacity by improving mesoporosity and pore structure. It's our experimental design. You can see it's completely randomized block design, and it was established in 1997. We have 4 different treatments: weedy fallow, that is no treatment, like control, compost, manure, and cover crop. I collected soil sample from 2 different depths, 0 to 20 and 20 to 40 centimeter. We applied gramoxone and atrazine herbicides, and a different mixture of cover crop seeds were applied in cover crop treated plots. Compost and manure were applied at a rate of 15.33 megagram per hectare and 23.3 megagram per hectare respectively. Corn population was 76,006 per hectare, and we used tractor from John Deere and planter from John Deere as well. I used cone penetrometer technique to measure penetration resistance. Undisturbed soil core method were used for bulk density measurement. Particle density was measured using pycnometer. Plant available water capacity was measured using pressure plate techniques, and soil organic carbon using CN elemental analyzer. Let's talk about some results. You can see the bulk density and penetration resistance shows same kind of relationship here. It's like for compost, it is showing that compost, for specifically the surface layer, the compost reduced the bulk density significantly compared to the fallow. For total porosity, it shows the opposite result as we are expecting. So to talk about the mechanical insights, organic amendments like compost manure could improve soil structure, and it could also enhance porosity. Soil organic carbon, it's doing very great for compost and manure compared to the fallow. For surface layer, manure shows significantly higher soil organic carbon, and for subsurface layer, similar kind of trend were shown here. For fallow, like that showed the lowest soil organic carbon toward the plots. And organic amendments such as compost and manure could significantly enhance soil organic carbon due to increased organic input and microbial activity. However, after getting this result, we went back to the field to understand the earthworm richness. And interestingly, we found that for compost and manure treated plots showed continuation of earthworm holes up to 30 centimeter. Let's talk about the pore size distribution. Transmission pores for compost, it shows comparatively higher transmission pore percentage compared to the fallow. And for storage pores, it's really like weird to see fallow show a much higher storage pore. So what could be the mechanical insights behind that? Fallow soil have higher storage pore functions, but fewer transmission pores, as you can see here, reflecting compacted but moisture retentive conditions that favor water storage over aeration. Manure and compost treatments improved both transmission pore and storage pore, and it's creating a balanced pore network or architecture. Plant available water capacity. For manure, it shows highest plant available water capacity. However, fallow also doing very great. So what could be the reason behind that? It could be likely resulted from low plant water uptake and enhanced surface retention rather than improved soil function and structural quality. It's one of the interesting things for doing analysis. It's called PF card. Alternatively, we can call it soil water retention card or soil moisture retention card. And it shows that the PF value, how we could define that. It's a logarithmic expression of metric suction. So we are considering metric suction for the y-axis, and x-axis shows the water content with volume percentage. And it shows that manure, the yellow card shows the highest water content for different suction rates. Volumetric water content at various sections that were measured using 3 categories: gravitational water, water available for plants, and unavailable water. And based on these values, we constructed the PF card. However, another mechanical insights could be as we are applying organic matter in the soils, most importantly, manure and compost treated plots, it shows something very positive with microbial necromass that could improve, that could help to bind clay particles and iron aluminum oxide that could form mineral associated organic matter that is more stable compared to the labile carbons. Depth-wise relationship between storage pore and plant available water capacity, it shows that for A, 0 to 20 centimeter depth, strong positive correlation. For 2 subsurface layer, that is also showing that similar kind of trend. The strong linearity indicates that surface structural improvement under organic management directly translate the higher plant available water capacity. For depth 2, the subsurface layer, it shows the higher R-square values that could also indicate the storage pore are the dominant physical determinant of soil water availability. These overall results could also confirm that soil compaction and total pore volume are critical for plant available water capacity. The limitations could be site and soil context. We have limited specific soil types and specific climatic conditions. It could be one of the limitations for our work. However, the future research would focus on multi-site and multi-soil variation, linking plant available water capacity with ecosystem services, and applying remote sensing and artificial intelligence. To conclude, long-term organic amendments under no-till significantly improve plant available water capacity. Manure improve the best balance between water storage and release. Fallow released water most rapidly, lacked structural and functional integrity. These are the references I used throughout this presentation. I'd like to thank Low Carbon Center and all of my PhD committee members. And I'm really grateful to the C Forum sponsor. And finally, I'm really happy for all of you to be present here. Thank you so much. If you have any questions, I'll be happy to answer.